the final fight, preliminary run. So this is the final run of round 5. And so in this round 5, we have this special rule. The problem reported already be decided beforehand. So the first stage, the reporter would like to report problem number 3, which already shown on the screen. And so, but before the fight, I would like to introduce the juries. So we have the Professor Ye Wangqi from Donghua University, and Na Yanwen from National Taiwan Normal University, Ren Jilin from National Taiwan Normal University, Cai Zhizhen from National Taiwan Normal University, and Lin Junliang from Jiaotong University. And now it should be Yang Ning Jiaotong University. Okay, so we will skip the challenge and start directly from the preparation. So you have, I think it's 4 minutes. 5 minutes preparation, please. And also, each team should write down the name of representative on the blackboard.
Okay, I think I'd like to begin my report. So good afternoon, everyone. My name is Jonathan Bruce. I am reporting problem number 3, proximity sensor for Team All-Nighters. So let's begin with the problem statement. A simple passive inductive sensor can detect ferromagnetic objects moving through its magnetic field. Construct such a passive sensor and investigate its characteristics such as sensing range. So we feel that the main focuses of this problem are how does an inductive sensor detect ferromagnetic objects, how can the position of the object be accurately measured using this sensor, and what parameters affect the sensor's characteristics like sensing range. So here's an outline of my presentation. I'm going to go through an introduction where I consider ferromagnetism as well as permeability and induced magnetic field due to the presence of the ferromagnetic object. And then I'm going to go through a theoretical model where I consider inductance as well as the relevant parameters to test. Then I'm going to go through experimentation and discussion, including the circuit design and analysis methods, and finally a quick conclusion. So let's begin with the introduction. So here is a diagram of a proximity sensor coil. Here you can see the red represents the coil as the inductor in the circuit, and the blue represents a ferromagnetic object or just any object being placed inside of it. So you can see that when a current flows through a solenoid, we know that it generates a uniform magnetic field inside the solenoid. And if a ferromagnetic material is placed into this field, then its domains will realign to the field. We know this is a property of ferromagnetic materials. And this induced magnetic field from the realignment of the ferromagnetic material's domains then creates an induced current in the coil, and this allows us to detect the presence of the material. So let me speak a little bit more to the permeability of ferromagnetic materials. So we know that if a material is ferromagnetic, then its domains will tend to realign with an external magnetic field, and it can become strongly magnetized. And examples of ferromagnetic materials include iron, nickel, cobalt, and ferrite. In this presentation, we're going to be examining nickel and ferrite especially. And I'd also like to introduce the permeability curve that you see over there. This is the measure of how magnetized a ferromagnetic material can get in response to an external magnetic field that it's placed in. And you can see that the range we want to look in is the apparent permeability, where the magnetization responds very strongly to the external magnetic field, not in the range of incremental permeability over there. And by looking within this range, this will allow us to relate the induced magnetic field to the position of a ferromagnetic object inside of the coil. So now let's get into our theory. So we know that inside of a solenoid, without anything inside, placed inside of it, just a solenoid, the magnetic field is going to be the permeability of air times the number of windings of the coil times the current passing through the coil. And when we place a ferromagnetic object inside of the coil, we're going to assume that that this magnetic field is going to increase by a factor of K, because the permeability will change by this factor. We assume that the permeability of the ferromagnetic object is so high that once it's there, its permeability is significantly higher than that of air. The permeability of air becomes rather negligible. So then we can then relate this to the percentage of the total volume of the ferromagnetic material that's inside of the coil, because that allows us to measure the position. Only the part, we're initially assuming here that only the part of the ferromagnetic material that's inside of the coil actually becomes magnetized. And then because the volume is of course the area times the length, we can then relate this to the length of the coil, percentage of the length of the coil that's inside, and then we can calculate a formula for the permeability of the rod as a whole, combining both the magnetized and non-magnetized parts. So then we can model the coil as an inductor, and we can see that the inductance is going to change when the rod is inserted. The L is going to be the inductance without anything present, just the coil, and the mu rod times L is going to be the added inductance due to the presence of the ferromagnetic object. And we already know what the permeability of the rod is. We just derived it on the last slide. So we can plug this in, and by combining a couple of constants, we can obtain this equation, where we see that the change in the inductance of the coil is proportional to the amount of the rod that is inserted into the coil. So now let's go over our circuit design. First of all, these are just the ferromagnetic materials that we've chosen, namely ferrite and nickel. And here is the RL circuit that we designed to measure the inductance. So we can see on this slide, so you can see using Kirchhoff's laws, we can determine the voltage across the inductor here, which is going to be L di dt. So we can then quantify the time constant of the inductor, and this video is just showing how when you insert the ferromagnetic material into the coil, then you can see that, replay the video please. Okay, well, if you watch the video, you can see that the time constant is going to increase, so the inductance is going to increase. Yeah, you can see that this is voltage across the inductor versus time as measured by an oscilloscope. So you can see the time constant, and therefore the inductance is going to increase when we have ferromagnetic material. So then, measuring this allows us to measure the position of the rod. So the first step experimentally is to measure the inductance of the coil without any ferromagnetic material placed inside of it. And so here you can see the voltage versus time curve for the coil that we used. And this is with a ferromagnetic object inserted at various lengths inside of the coil. So for example, inserted like, for example, 2 or 4 or 6 cm inside the coil. And of course we're looking at when it's not inside the coil here to determine just the inductance of the coil. And by calculating the time constant, we can determine that that's 1.76 millihenries. So then we can look at the position of the ferromagnetic rod versus the inductance. So as we stated earlier, the inductance is linearly related to the position, to the amount of the rod that's inside of the coil. And intuitively, this means that the more the rod is inside the coil, the more magnetized the rod is, and this increases the induced magnetic field and strengthens the current in the coil, therefore increasing the inductance. And we can see that this aligns rather well with our experimental data as shown there. You can see that here, the ferrite position, a negative position is representing the distance that the tip of the ferrite rod is outside of the coil. And then, of course, positive positions are when it's going inside the coil. So you can see a pretty strong linear correlation there. And we also examined the material, ferromagnetic material versus the inductance changes. And we can see that the inductance is positively correlated to permeability, because the more permeable, if a material has higher magnetic permeability, then it's more easily magnetized, and this creates a larger induced magnetic field, which strengthens the current and inductance even more. So we can see that we have nickel and ferrite here. And compared to ferrite, nickel has a rather small permeability, about an order of magnitude smaller. And we can see that this aligns very well with our experimental results. You can see that, in fact, the calculated ratio of the permeabilities is about equal to the ratio of the textbook values of permeabilities. So our experiment works rather well for this. However, we did notice some unusual phenomenon in our experiments, namely the concept of sensing range. So what we expect from our theory earlier is that the detection of the object only begins as it's being inserted into the coil. But what we actually observe is that the inductance changes slightly even before the rod is inserted. So you can see this here, it's increasing even when it's about 4 or 5 centimeters outside of the coil. So we performed a couple of experiments to measure the sensing range as well. So we know that the current and the magnetic field of the coil are directly proportional. So this means that by changing the voltage applied to the entire circuit, and therefore changing the current, we can observe a proportional relationship between the sensing range and the voltage applied. And this is because the stronger the magnetic field, the further away from the coil the rod can be in order to still be detected. And we also measured this as a function of coil density, as we also saw from the formula for the magnetic field inside a coil. The current in the coil density, number of windings, and the magnetic field are also directly proportional. And we again observe a linear relationship for our sensing range when examining this. So this allows us to correct our theory a little bit. So now we can add in the coil sensing range into our theory. So we can see the linear increase in inductance now starts before the ferrite is inserted into the coil. And this gives us a better correlation with our experimental results as observed there. So now as for our conclusion. So to reiterate, the conceptual understanding is that the ferromagnetic material in the coil creates an induced magnetic field, which enhances the current in the coil, which increases the coil's inductance. And we are able to measure this inductance versus the positions of the rod inside the coil. And we saw that the magnetic permeability of the material versus its position was a linear relationship, and we were therefore able to derive a final equation for the change of inductance versus time. And in our experiments, we tested the inductance versus the distance that the rod was inserted and versus the permeability, and we found very good correlations with our theory. And we also modified our theory by including sensing range as well, and tested that with the current slash voltage as well as the coil density. And some future steps that we acknowledge we could take after examining this are to develop a slightly more quantitative theory for sensing range in order to predict that, as well as incorporate the cross-sectional of the material. Thank you very much. This is my report.
All right, so I'll follow your 2 minutes first question.
We are team erudition. Now I have some questions for you. First, did you include the voltage in your inductance?
I'm sorry,
did you include the voltage or power to your system of your experiment equipment?
Perhaps I should explain. We had a constant
Yes
source
or no?
so we had a constant source of.
Yes or no, please.
Yeah.
Yes.
Yes. Yeah.
So the problem statement says the.
I'm not sure I understand the question. Could you please reiterate the question, please?
Okay. Repeat the question.
Yeah, thank you.
Did you input any voltage or power to your system? The experiment equipment you use.
Did we input any voltage? Yes, yeah, we had constant voltage being applied to the circuit.
Okay,
Yes.
next, what's the material you use to sensing the objects?
As I stated, the two materials, ferromagnetic materials we examined were nickel and ferrite.
Poor nickel and ferrite.
We examined a nickel rod and a ferrite rod.
Poor or alloys?
Just pure.
Okay. Next question is, how many times do you do your experiments?
Well, we repeated a sufficient number of trials, and as you can see, our data correlates very well with our theory. We could have repeated some more trials for some of our experiments. For example, you can see here there's a bit of error because we only did a lower number of trials for these, but we could.
Okay. Did you think the velocity of the object moving will cause any difference experiment data to your experiments?
Yes, however, these were all mentioned when these were all measured when the object was stationary. We were only looking at detecting the position,
Okay,
not the
thanks.
velocity.
All right.
statement, and I think I think there is some key point. First key point is we need to ensure the mechanism, and the second point is the rebalance of the parameters. Yes. So here are some brief review. First, there are some pros of the observation. A short observation video that can clearly demonstrate the phenomena, and also there are some cons like the sensor is not passive since they input a power into the system. And well, the problem statement says we need to structure a passive inductive sensor. So I think there are some problem in your experiment or something. Oh, next. Here are some brief review of the theory. First, there are some pros of the situation to present the theory and clear background explanation for equations, and also some cons like ignore some parameters such as the velocity in which the magnetic object is being injected into the coils. And the setup has some pros like have a good idea of assembling experimental equipment and speak clear. And also some cons like the reporter gave the sensor input voltage, thus making it not passive. So the experiment has also has some pros like a very detailed explanation and some correct to the experiments. And also has some cons like problems that the sensor should be passive. However, voltage is being input into the sensor, so which doesn't fit the current statements. And I think the experiment data graph has some low R-square value, like that's 0.91. I think it's pretty low, and it's too small for experiment to be considered accurate. And the conclusion: this is a report well structured and so for in many ways. There are still a few flaws we would like to point out. First, the certain parameters were ignored, such as the velocity in which the rod was inserted. And second, the accuracy itself is unable to convince people that the theory is correct. And the passive sensor is not actually passive as voltage is input. So when it comes to accuracy and precision, we are sure that these are points that we would matter the most. So now I'm going to ask some questions.
Jump to the discussion.
First, I want to ask you some questions about the passive. What do you think about the passive inductive sensor? The passive. How do you define the passive?
Okay, well I think that our setup here is good for quantifying certain key characteristics as well as for controlling certain parameters that are relevant to the experiment.
So how do you define the passive of the problem statement?
Well, I think that this setup fits the problem statement well. Even though
it's not positive, you know. You input the voltage, the power, so it becomes not positive.
Okay, so I see what you're saying. So perhaps some of these things could be applied to a non-passive system, but we think that this is a good way to model the phenomenon.
So you think your system are not positive?
Well, I think that our system addresses the problem statement, which we believe the main focus is on inductive sensing.
Okay, so second, I want to ask do you know the eddy current?
Eddy currents, you mean within the ferrite rod that's being inserted? Or?
But I think the material is put into the magnetic field.
Yes.
So the magnetic, oh sorry. And next question. But I think go back to the problem statement. So I think the passive sensor need be passive because it didn't input any power or voltage. So, okay, what do you think about it? I think the passive this word is really important because the problem statement is right on there. So, did you any misunderstanding the problem statement?
Okay, I understand where you're coming from, but still I think that this is a good model for the problem statement because this is indeed an inductive sensor that detects from magnetic objects, so I'm not sure.
But it didn't passive.
Well, again, I think this is a good setup for modeling that. I think that, sure, you have a point there, but I think that we still address the problem statement quite well.
Okay, so, and then, how do you explain the R-squared value is too low?
Okay, so I should probably clarify. So for these, we only did a couple trials. So this is probably also due to experimental error. And unfortunately, our oscilloscope that we used to measure the voltage versus time graph that I showed for the inductor, it wasn't able to easily connect to a computer in our trials, so we did have to do a bit of like slight visual estimation for when the inductance began to change, so when the sensing started. So there was a bit of error built in there, I should clarify.
Also,
Yeah.
next question.
If we were to repeat the trials a lot more times, we'd probably see a lot better data.
Well, did you think the velocity will affect the experience data you just said, and how did it affect it?
Okay, so that is a very valid point. I should clarify that all of this data is collected when the ferromagnetic object is still. We are not considering the ferromagnetic object's motion with our equations or with this data. However, we did run a couple of observational trials where, as shown in the video, we moved it. And in the case of the motion of the ferromagnetic rod, due to Lenz's law, it could induce a magnetic field that's opposite the magnetic field of the actual conductor. But in our trials, we observed that this opposite magnetic field is very, very small, and that the most predominant phenomenon was still the magnetization.
Now, did you think there is any deviation in your experiment? Can you explain this? Any deviations in your experiment?
Deviations from what? As in data deviations from the expected?
Yes. Like okay, just say.
Well, I mean, as I already explained, some of this error is probably caused by just errors in our setup that we can't control, like having to visually estimate when
So
the
you
sensing
can
is.
control the deviation in this experiment?
We could control it by running a lot more trials, or by perhaps getting an oscilloscope that can connect to a
So
computer.
did you control the deviation of your experiment?
Well, we tried as hard as we could to control the deviation of our
You
experiment.
tried, but the
yeah.
R-squared value is still 0.83.
Okay,
So
well,
it's pretty low.
okay, I acknowledge that there are ways that we could have improved our setup, but this was what we could do with the equipment that we had, and we think that it still is able to demonstrate the
So did you
relationship
think
with
the
shell.
R-squared value is only 0.83 is accurately enough?
Well, we think that given the certain inaccuracies of our setup, and given the much better correlations observed, for example, there, we think that our experimental data as a whole it does demonstrate the relationships that we're trying to prove.
Okay, and the next question.
And again, we acknowledge that there are certain inaccuracies. We would like to be able to control these. But
Well, I want to know what inductance in your experiment you use. Did you show any photos?
What inductors we use?
Yes.
For example,
What kind of inductors?
well, we just use coils of wire. We use solenoids.
You use a coil of the
Yeah,
wires?
yeah, that is our
Okay.
inductor right there. We measured the inductance of this particular one to be 1.76.
Okay. Did you think you there's any effects will cause to change the inductance value in your experiments?
Well, as we said, our entire theory is based on the insertion of the rod changing the inductance value. So I'm not sure what you're asking.
Another effect.
Another effect?
Do you think there's any effect?
Well, I think that the two main effects at play for the inductance are just the natural inductance of the coil itself, and then the changes due to the presence of the ferromagnetic material.
Did you ensure your inductance is really what inductance value you use in your experiments?
Well, as I said, we measure the inductance of just the coil itself without any ferromagnetic material present to be this value. And then we measure the changes from this value in graphs like these to determine how it changes.
And next question, so you only use the nickel and the ferrite only in your experiment?
Yes, and you can see the comparison.
Only use these two objects?
Yes, we only use those two objects.
But why? You can use another magnetic objects.
Well, because because first of all, that's what we had access to, and second of all, we think that these represent two very different types of permeabilities, so we can very clearly demonstrate the effect that permeability has on the data. You can see that the permeabilities are very different by about an order of magnitude.
Okay, so did you think if I use the like nickel alloys will change this experiment data, or
probably
I use
because that would
right alloys?
well, probably because that would change the permeability of the material, and then that would certainly change the slope of that line and how much the inductance changes.
How did you know it will be changed? You didn't do any experiments to prove this.
But we did. These are two
But
experiments.
you didn't
with two
do
different
any
permeabilities.
experiment about any like nickel alloys. You can say that experiment data will be less. You didn't do these experiments.
Okay, well, we didn't do the experiments, but we do know that the permeability would be changed, and we've already quantified how the permeability affects the data. So our theory is able to predict this, and we have demonstrated different permeabilities here.
Okay. We'll go back to the problem statement. The problem statement here says the object was moving, but your experiment data only use the object was stopping. So
Okay.
the problem statement is there. So what do you think about this?
Right. So the data that we're showing here is with the object stopped. However, this can very easily be applied to the object moving, because the oscilloscope that we use, you can see the video that we showed earlier, if I can just play it here. You can see that the oscilloscope is able to very accurately measure changes with a high sampling rate. In fact, the frame rate, the sampling rate of this oscilloscope is about 800 times higher than the actual time constant of the inductor that we used in the experiment. So essentially what this does is it just measures it point by point by point, very, very fast.
But I think the magnetic flux will be changed because your object was moving. So the magnetic flux will be changed. So your data was not accurate.
Okay.
It peaked off when the object was moving.
Okay, well, as I mentioned, we did take Lenz's law into account here. We do know that when it's moving, it will produce a bit of an opposing magnetic field. But as I said earlier,
But I think in the different velocity of the object will change the experiment data. So you didn't do these experiments, right?
okay, but as I said, everything that we were doing can be applied to a moving object by
You do
measuring
this.
it at.
You do the object was moving and your observe it.
Okay, we did not explicitly test that, but we
So you
did do some
didn't do
trials.
this experiment, right?
But
But the problem statement here are saying the object was moving through the magnetic field. But you didn't do this.
Okay, but the point is, everything that we're doing can actually represent that. In fact, as we showed here, it's a very good representation of that.
But your
If the sampling rate of the oscilloscope is high enough to catch it at every single point as it's moving through, which our oscilloscope could do, because it was an industrial grade oscilloscope.
but you still didn't consider the velocity of the object was changing.
Well, we agreed that we could have tested it as a parameter,
Okay.
but as I stated, our experiment is,
Okay,
our
okay,
theory is
okay,
still
okay.
applicable to this.
Well, I think I finished my discussion. So
you want 1 minute to summarize the discussion?
first, the problem statement says we need to construct a passive inductive sensor, but I think the report didn't consider this because it input the voltage into the coil or its system. So I think it's not passive. And then and I think the report should do more experiments like the velocity changing or the other materials, and it will be more better to their report. Okay, thanks.
For reviewer, the question to the
Okay, to the recording and also to the opponent. And as the opponent has mentioned many times of the definition to the passive sensor, I want to ask the reporter, so is your sensor passive?
Well, we admit that we are applying a voltage to our
Okay,
sensor.
so do you think that your device is the passive sensor, as the Franzman has mentioned about?
Okay, well, we admit that our particular device was applying a voltage, as the opponent pointed out, but the theory and principles that we used here could also
So
be
you have
applied to.
generated, so you have given it a power or given a voltage in your device, right?
Yes, we have.
Okay, so and just as the opponent has said, that isn't a bit problem statement. So do you think that it is possible that your sensor that you have constructed is not a sensor problem statement mentioned?
Well, we think that this demonstrates the principles that are necessary for a passive sensor. We think that this could be adapted to, for example, a passive sensor like an LC
Thank you
circuit.
for your explanation. And how does your opponent think?
I think a passive means we don't need to enter. We don't need to input any voltage or power.
Okay, thank you. And to the report, I want to ask you that if your sensor can only detect one-dimensional motion, is that correct?
Well, yes, it only detected one-dimensional motion. In fact, we tested at a constant position. We tested moving it up and down and side to side, and there was no change.
So how can you just distinguish the change of the magnetic flux in different axes? Just
Well, because we said the magnetic field within the solenoid is uniform, so it doesn't matter where it is in the solenoid as long as it's not
okay,
way
thank
too
you for
close to the edge.
explanation. And I want to ask you, do you think that the magnetic force would affect the motion of the object? How would it affect?
Well, as we mentioned, if it's moving, there is a very small opposite field due to Lenz's law, but this was very, very small in the experiment.
Okay, thank you. Then, how to
Could you repeat the question?
do you think that the magnetic force would affect the motion of the object? The magnetic force. Yes. Okay, thank you. So the reporter, when a magnetic object is moving, a inductive voltage would be caused by the Faraday's law. So how could that affect your experiment?
Well, as I already stated, we took this into account, but we noticed when we were moving the object, we could barely even observe this phenomenon on our
So do
oscilloscope.
you consider that in your theory, or just you have considered that situation?
Well, we considered that qualitatively, but we didn't include it in our theory.
Okay,
because
thank
we
you.
thought it
Then
was
how did the
negligible.
opponent think?
Could you just repeat it?
It's okay. When a magnetic object is moving, an inductive voltage would be caused by the Faraday's law. So how would that affect the experiments of the reporters? How do you think?
I think.
Okay, and so the reporter, as you can see that the inductive only have a significant change after entering the coil. So it's the motion of the object is not able to through your device, which the sensor you have constructed.
Oh, I'm sorry, I didn't understand the last part of that question.
So as you can see that your inductive
I'm
only
sorry,
have
time's
a,
up. Time's up.
thank you.
Switch the connection.
So under technology computers, I'm the reviewer from the same cells here, and the problem statement I'm going to review is problem statement number 3, proximity sensor. So this is a problem statement. A simple passive inductive sensor can detect for a magnetic object moving through its magnetic field. Construct such a passive sensor, investigate its characteristics such as sensing range. And this is the report's outline. First, the phenomenon he has discussed about it in induced current happen, and in the theory part, he has discussed about the relationship of magnetic field and induced current B field, H field, and magnetic permeability. And in the experiment, he has shown his setup, and also he showed his data analysis, and also the distance, and what is the coil. Then this is the pros and cons of the reporter. First, he has a clear explanation about the phenomena since that observation video, and also has tested numerous parameters in his experiment, and it has a high accuracy. But the cons is that the video is not clear, so that we couldn't observe it clear, obviously, and also has a misunderstanding about the prompt statement which I mentioned about the passive sensor. And we didn't consider the characteristic of a sensor, and also the theory was too brief to explain the phenomenon. Then this is the opponent's outline. First, and in his summary of his presentation, he has the definition of a passive sensor, and also he discussed about the velocity of ferromagnetic object. And this is the pros and cons of the opponent. The pros is that he pointed out the reporter's mistake of definition, and he also corrects concept about the passive sensor, which I just mentioned in the prompt statement. But the cons is he has too much discussion toward the meaningless points, and also he didn't give in straight questions that this question is too long, and also he has no opinion explained. Then this is a discussion between the reporter and the opponent. First, the opponent asks how to define the passive sensor, and the reporter says our experiment is fits with the prompt statement. But the reviewer believes that we think the reporter has misunderstanding about the passive sensor, and he is escaping questions. So we agree with the opponent very much. The passive sensor should be defined as sensor with no storage energy, which is very important that the prompt statement has mentioned about. Then this is our second discussion about the moving object. The opponent asks, the problem statement mentioned the moving object, and the reporter says that it can be sensed after measured point by point. And the reviewer believes that the way he can sense moving object with the furthest law fits more. And also the furthest law didn't apply more in the theory about in the reporter's report. Then it's our third discussion about the experiment. The opponent asks, there's no experiment toward moving object and sensing range. And the reporter answers that the experiment is able to demonstrate the result. And the reviewer believes that, strongly disagree with the reporter, that the sensing range should be a key factor in this experiment, which is very important that we should investigate about. Then this is our point is that in the discussion between the reporter and opponent. First is the definition of a ferromagnetic object, which is very important because we have to consider about the magnetization. And also the boundary limits of the sensing range, which is affected by many factors, such as the environment, noise, and also the windings of the coil, and also the change other factors. And also the third point that we have missed is the initial magnetic field included in the device. Also, the relation between the B field and the H field and how they affect the experimental result is not discussed in the discussion between opponent and reporter. And finally, his theories is any complex relationships between the magnetization and the magnetic field entity or ferromagnetic object is not well discussed in your discussion. And this is my presentation. Thank you.
On the reporter, you have to wait to conclude.
Okay. So thank you for the opponent for a fruitful discussion, and thank you to the reviewer for pointing out some additional issues. I'd just like to clarify a few things. So it appears that there was a lot of discussion about the nature of a passive sensor, and I agree that in our experiment, we did apply an external voltage to the system. However, that was merely for better control over the current in the system. We could just as easily demonstrate this phenomenon using an LR circuit or an LC circuit without an external voltage source, and our theoretical assumptions and equations would still apply. In addition, there was some concern over the motion of the ferromagnetic material as it was passing through the coil, and we stand by our assumption that we can use our equations and measure point by point using our very high sampling rate oscilloscope in order to determine this. We do acknowledge that there is going to be some inaccuracy here due to Faraday's law, but we observed in our observational trials using a moving ferromagnetic material that this was not going to be very significant for us because the magnetization of the ferromagnetic material appears to be more significant in our own experiments. And there was also some concern as to the sensing range and as to the accuracy, and I believe that we tested a robust set of parameters here. We agree that we could have tested more parameters, such as, for example, the velocity of the object, but we think that we were able to verify our theoretical assumptions and show that our theory represents this problem quite well. So thank you very much.
Okay, so you find the project on the jury.
Okay. Yeah, I have 3 questions for each of you. Firstly, for reporter, if I have non-magnetic object, do you think can you detect it or not?
Well, we think that the detection, as we said, the main factor is the magnetization. So it depends on the magnetic permeability
Yes
of
or
the material. Well, if it's not magnetic, well, if it doesn't have a very high magnetic permeability, then no, not really.
No? There is thing? Yes or no?
Sorry, may I discuss with my team?
There is thing? Yeah. In this setup, that can detect non-magnetic.
Sorry, may I discuss with my team? So, should the opponent answer first?
No. Can you use your response yes or no?
Chair, may I answer the question for my team?
Okay. Okay. Okay, so you can
I
respond.
think it's not, no, yes,
No?
no.
Can I repeat again?
Chair, can I please answer the question for my team?
I think he's the answer the question. You can discuss, but representatives the answer.
Okay, thank you. So at first, I think the professor, can you repeat your question again because we didn't understand very much.
Okay, so if I have non-magnetic object, okay, non-magnetic object, do you think you can detect it or not in this setup?
No, we can't. No.
Okay.
Thank you.
Okay, so I think there is an argument about the cases and also its magnetic field. So I just want to ask also him, I mean the magnetic field of what? The sensor or the ferromagnetic object. So let's start
Could
with.
you repeat the question again?
Okay, so the problem statement saying that to detect the ferromagnetic object moving through its magnetic field, right?
Yes.
So the magnetic field of which item is that it means that the ferromagnetic object or the inductive sensor.
Well, I think it's inductive sensor.
Okay, and it's passive, and you say that there's no energy and it has a field.
Well,
Then okay, then
Okay, I think it's the sensors. It's by the inductive sensors.
so the field is from the sensor,
Yes.
and
there's
you
no,
think it's passive and
no source energy.
no source energy, and it still have a field.
Yes.
Okay, and then
I would agree that as in our theory and experiments, it is the sensor.
with the
Yeah,
sensor.
yeah, I'd agree with the opponent reviewer.
So, questions? So it's time for jury to pick, let's have the point for the reporters. 7, 8, 6, 7, 6, and 7.
Thank you.
And for the opponent, 7, 5, 7, 6, 6, and 7.
thank you.
And for the reviewer, 8, 7, 8, 7, 8, and 6.
Thank you.
So any professor like to comment? So if not, let's close this on stage. Thank you, everyone. So we have on this slide, and the problem to be reported is problem number 9. And reporting of 5 minutes to finish. And also each team write down the name of the representative on the whiteboard.
Alright, so greetings everybody, I am from Team Erudition and this is question number 9, Light Whiskers. Let's get right into it. Okay, first of all, this is our outline of the presentation. We have 5 parts and just read it yourself. Next.
First of all, introduction and observation. This is a problem statement. When a laser beam enters a soap film at a small angle, a rapidly changing pattern of thin branching light tracks may appear inside of the film. Explain and investigate this phenomenon. We have 2 key points. First of all, we have to discuss the mechanism, and second, we have to discuss the ambient conditions. Okay, so these are the observation videos. As you can see, the quality is a bit poor. When the light passes through the bubble film, it causes some kind of refraction. We will discuss this mechanism later. As you can see, in both the videos, it has branching lights. Now, for the theory part. First of all, we have to discuss the structure of the soap film that causes different refractive index. As you guys may know, the refractive index is a comparison of the sine theta in which the light refracts through different matters. So with thicker soap film, you have a higher density of surfactants, and then you have a larger refractive index in which and water is about 1.33. The thickness changes in larger interval, and then you would have smaller changes of the refractive index. Now, the structure of the soap film may cause different refractive indexes. As you can see, if you have a thicker one, you have a larger refractive index. If you have a thinner one, you have a smaller refractive index. And this is the diagram basically just interpreting the whole thing. Now, correlation length. If it's larger than wavelength of the incident light. In smaller scales, the adjacent area may not have large thickness differences. That is not what we want to see. But if the variations in the thickness between position A and position B are independent, then we call that distance between A and B the correlation length. So the branching light tracks appear when the correlation length is larger than the wavelength of the incident light. Now, a phenomenon that may be observed. We want to look at caustics, light incidence through a mirror-like medium, which is the soap film in this case. You either have reflection or refraction or both of them, and then you have a diffuse reflection on the surface as seen right here. When it reflects and then reflects, that's diffuse reflection. You have dark and bright areas in the observer's eyes, and this one is brighter because it has much more light concentrated on it, and this one is stronger. As you can see, it only has one ray of light. Now, thin film interference. We have to measure the thickness of a soap film to discuss this as a relevant parameter. So we use TFI. We can actually discuss light waves reflected by the upper and the lower boundary as shown in the previous diagram of the thin film may interfere with one another. Thus, different thicknesses can lead to different wavelengths of reflected light. As you can see, the RGB color correlates to the thickness in nanometers. This is the whole diagram, and we will use that to interpret our experiment later. Now for the setup. Okay, so the shooting of the soap film, we have a camera, tripod, soap film, tripod, laser beam, which is our incident light that we're going to use. That one was like a flat soap film, so there's only one layer. Convex soap film means that there's like a 3D bubble thing. The laser beam, soap film, camera, and then that's the soap film and the heating plate, which we will discuss why we need that heating plate later. Now, the shooting of thin film interference, we have a artificial daylight, and then we have a lamp, and then soap film. Yeah, that's very obvious. Experiments. Okay, so experiment 1, basically want to control the concentration of a soap film and the shape of a soap film. So when we get the thickness of a soap film, we can measure the branching width, we can measure the maximum branching angle, and the photos of branch light tracks. For experiment 2, we want to discuss the temperature of soap film. Same thing. Experiment 3, we want to actually know what the wavelength of our incident light is. Now, we have different concentrations, five different concentrations, water, detergent, glycerin, that's what we use. Different shapes, we have a flat soap film, 5 times, and then we have convex soap film, which we shot through top, middle, bottom 5 times each. And then we can measure with software. Measuring the thickness of the soap film by TFI, we use flat soap film 8 times for each concentration. Convex soap film we divide into 8 parts, which is different angles. We measure the RGB value and then display the variations of the thickness. Now, concentration 1, water, detergent, glycerin 3 to 1 to 1. Basically, these are the results. You can see that the maximum width is, first of all, the branching width is basically about right near 1, and then the maximum branching angle is like 10 degrees, 20 degrees, 30 degrees, and then back to 20 degrees, the average. Yeah. Now, for the flat cell film, these are the things that we saw. You can see the lights are actually branching, top, middle, bottom. That is what the whole bubble, the convex bubble. Okay, now, concentration 2, we have 3.5 to 1 to 1. And then the average width of the flat cell film is 2.64, and the maximum width of the cell film is 4.01. And then we have the convex cell film maximum width right there, just read it yourself. Maximum branching angle is, for flat, it's 49.42, and then there's the maximum width for top, middle, bottom, and then average. Yeah. Okay, so now basically you can still see that we have the branching angles. This one, yeah, specifically, and then the top, middle, bottom for a convex cell film. Yeah. Okay, so this was basically the same. We're just like kind of messing around, right, with the concentrations right here. So yeah, maximum width 3 and the maximum angle 39.95, which is basically 40 degrees. Maximum width, yeah, basically still about between 1 and 2 and slightly under 1. Maximum width is, yeah, just read it yourself. Okay, so same. We noticed something weird about here because it like curves back, and it is also like kind of curves back. Yeah, and for the convex cell film, it's basically pretty much the same. Now, concentration 4. You know what? Just skip this. The experimental results are basically not really that different. Yeah, skip this too. Now, for different concentrations and shapes of the cell film, when the cell film thickness is increased, we notice that the branching width increases, and more branches equals to a larger branching width, which you can see in this diagram itself. Now, as the maximum branching angle decreases, you can see the thickness changing in a smaller thickness interval, and the thickness changing in the larger thickness interval. You can see the interval difference right there, and then the average thickness right here. Oh yeah, and that's the one we use for the end. Yeah. Now, for the convex cell film, it's basically another graph, and then we know that the thickness increases from top to bottom, basically because it distributes. Larger changes on the bottom of the cell film. Yeah. It's thicker on the bottom with more branches, which equals to larger branching width, and on the bottom, there's larger thickness variation, and then also a larger branching angle. You can see for yourself these diagrams. Okay, now the special curve deviation on the convex cell film. Large and quick changes of the thickness equals to continued deviation in a small distance. You can see it's like it just flicks around. Now, experiment 2, different temperatures of cell film. We use 25, 50, 100, and 150 degrees Celsius. That's what the heating plate is for. And then we analyze this everything 5 times. Yeah. The maximum branching angle is 30.46 degrees, and then the maximum branching angle right there is 41.88 degrees, and you can see for yourself these pictures. Okay, the maximum branching angle for 50 degrees top is 64.96, and then for middle and bottom it's 46.39. Okay, for the top it's 47.18 degrees, and yeah, so basically for middle and bottom 100 degrees it's really hard to form. Now 150 degrees, we assume that the temperature is simply just too high to form any special thing. Now, experiment 2, different temperatures of cell film. The reason why branch slides is hard to film at large temperature because you have a large perturbation velocity at high temperature, thus the thickness of the cell film is uniform. So the branch slide is hard to form, like what we mentioned earlier, caustics. Temperature variations on the top and middle and the bottom of the cell film. Well, in the top, if we have higher temperature, we have more curve deviation, and then we have a larger branching angle. Well, if the temperature is too high, you can't form anything, as I mentioned just on the last slide. Okay, oh no, come back. Yeah, near the heat, middle and bottom, it's near the heating plate, so basically it's just hotter. And then the branch light, it's hard to form. So now we tested different wavelengths of our incident light. So basically we have red light and then we have green light. 495 to 570 nanometers and 620 to 750 nanometers of light. So it's kind of hard to let the correlation length to be larger than the wavelength of the incident light. So we know that the middle and the bottom part of the convex cell film has larger thickness variation. The top part of the heated cell film is easier to form an uneven surface that creates this phenomenon. Now, for the conclusion, for the thickness, the flat cell film, when the concentration decreases, the thickness increases. Convex cell film, from top to bottom, the thickness increases. Heated cell film, the upper part thickness is lower, and the bottom part thickness is higher. The wavelength for everything, when your wavelength goes down, the branching light is hard to form. And for the branching width, the flat cell film, when the thickness increases, the branching width increases. And convex cell film, from top to bottom, branching width increases with the thickness. And for heated cell film, basically, yeah, branching width increases, and yeah. Maximum branching angle, thickness increases, and maximum branching angle decreases. From top to bottom, maximum branching angle increases for convex cell film. And then for the heated cell film, yeah, you can just see for yourself. Okay, that's all. Thank you.
Okay, thank you for the report. May I ask that how many times do you do your experiment?
Oh, we already mentioned that in the presentation.
Can you restate your?
Which one? Which experiment are you asking?
Every experiment.
Every experiment.
Are there
Try to experiment one.
Just an approx number, please.
It's right here. For the convex cell film, we divide it into 8 parts and 5 times of each, and this is just only for
So it's
this
40
kind
times,
of.
is that correct?
Oh no, that's just only for this kind of concentration.
Or
So
just
there's
5
kinds of concentration, so it's 200 times.
So can the bubble maintain for very long?
No. So basically, we have to remake every bubble.
So that how can we make sure that every time you make the bubble in the same condition, you get the same?
That's why we do error analysis and deviation. So
that-
basically, 5 times is just like a number. Basically, we do like 10 times for average.
Further discussion. And
Okay.
you have mentioned that you have changed the different components in your bubble. Is that correct?
Yes.
So does that mean that you are not able to know the components of the bubble?
I am not able to know the components of the bubble. Yes, we arrange the concentration of the bubble.
Okay, thank you. Can you please turn to page 14?
14.
Yes.
Yes, please.
You have 14. Thank you. And it seems that you have used a cell phone in your experiment. Is that
Oh no,
correct?
that's just a picture. We actually use the front page and the 13th page of the thing. We actually use this tripod camera.
You use a camera. So
Yeah, we
will
use a
the image affect the experimental result?
Will the image affect the presentation results? Of course, because the
Such as light
actually-
intensity or brightness? Will
Yeah,
the cell phone
because-
adjust it by itself?
the cell phone.
That
No, we
affect-
didn't use the cell phone.
Will the camera affect the experimental result?
Would the camera affect the experimental result?
Okay.
Probably.
Okay, I understand. Can you please turn to page 45?
45.
Yes, you have a lot of data, and is there any theoretical model to describe
Describe what?
the relation between them?
You can use caustics and TFI to describe it.
Okay, thank you. Honorable judges and fellow competitors, it's Team Excelsior, and today I'm going to oppose problem statement number 9, light whisker. The problem statement is that when the laser beam enters a soap film at a small angle, a rapidly changing pattern of same branching light track may appear inside a film. Inside investigate this phenomenon. And the main focus that the opponent believes that we have to investigate is the reason for the branching light tracks to appear and the boundary limit for the phenomenon to happen. Since that it is a very complex question, so the opponent made a structure of solving this problem. First, we have to identify the reason for the rapidly changing pattern of thin, branching light tracks to happen, including the film interference and the small incident angle, which is mentioned in the problem statement. Next part, we have to analyze the rate and the possibilities of the branching light beam appear in specific area, according to Snell's law and the calculation of possibility at the branching light tracks, which the opponents think that it is very important should be considered in the reporter's report. Finally, we have to investigate relevant parameters that affect the characteristic of the branching beam, which include the incident angle, which is mentioned in the problem statement, light intensity, and the thickness of the soap film, which is also mentioned in the reporter's report. And this is the strong and weak points of the reporter. First, he has phenomenological explanation about the branching light tracks, but his experiments lack of reproducibility and he has no quantified theory. For the next part, we have a clear setup about using the camera and the bubble, but his lack of experimental data and analysis of experimental data of graphs. And also, he has clear graphs which explains these phenomena, but the experimental result was not well organized and the deviation was not well explained. And finally, he lacked a relation between the degrees and the temperatures. And this is the points to be discussed that the opponent would like to mention in the further discussion. And first, about the explanation of the reason for such phenomenon to appear. For the branching light tracks, which is mainly caused by the dip inside the film, but the reporter mentioned that it is because of the different refractive index. And for the internal reflection, the opponent wants to ask about how did the reporter make sure the light entered the soap film. And also, the lens, which is the propagation lens and the correlation lens, which is mentioned in the reporter's report. The opponent would like to ask for further definition. And also, the rapidly changing film, which is affected by the flowing surface and the refractive index change. The opponent will also like to do further discussion. And for the boundary limits of the incident angle, since that the problem statement has mentioned about the small incident angle, so the opponent would like to ask, in what condition can the reporter observe such phenomenon to happen? And the wavelength, which will affect if the light enters the soap film or not, is also a key factor that should be considered in the reporter's report. For the random structure that is will affect the behind phenomenon, which is the branching light track, should also be considered. And for the experiment, the opponent would like to ask about the simulation and the measuring method of the possibilities by camera and the soap film continuity. And also, the pass-through films like tracks should also be quantified and observed. Finally, the theory, using the Snell's law and total internal reflections and the possibility should able to quantify the branching light tracks. Finally, the relevant parameters include the incident light, which will affect the boundary limits for the phenomenon to happen, and the direction of the light angle, intensity of the light track, and also the frequency will all affect the experimental result. Finally, for the parameters which is the characteristic of the soap film, the opponent believes that the thickness and the component that the reporter has mentioned about in his report will affect the whole phenomenon. And to re-emphasize the explanation part, the opponent believes that the definition of the lens should also be considered in the report. And this is the end of my presentation.
Go for discussion.
Okay, for further discussion, may I ask that, did you analyze the light intensity in your branching light tracks?
You mean the one that came out of the bubble or the one that shoots in the bubble?
All of them. Did you quantify them or analyze them?
Oh yeah.
Can you show me, please?
Oh, it's not in the presentation. We simply just
So we are not able to see the experimental result.
for the light intensity.
Yes.
No.
So
Yeah,
you
that is
cannot
something
prove
that I
that.
missed.
Okay, then can you predict that where's the point where it's the biggest light intensity?
Biggest light intensity
Yes.
for shooting out.
In the branching light track, where is the most biggest? Where is the biggest light intensity here?
Under what condition?
Chair, may we see that one, please? And the bubble. this is where the light is up, and it spread into branching light tracks. And where do you think that will have the biggest light intensity?
Is this light entering the bubble at a straight 90 degree?
Degree from where? I don't know.
Because see, here's the bubble. This is the flat surface that we're using.
Okay.
Right? This is the bubble. Oh,
Okay.
you know what? Let me just move on this. This is the bubble.
Yes.
So basically, we have this angle, right? And then we have
If it's
this line,
90 degrees like this.
90 degrees that literally just skims through the thing.
Yes.
The you know that the bubble is a double thing, right?
Yeah.
Does it just pass it through here and does not touch this?
It pass inside of the bubble.
Only inside of the bubble film. Does it pass through the whole bubble film itself? I'm trying to get a condition provided by you.
Yeah. Sure. Like this.
Like this.
Yes.
So basically, we think that when this happens, it reflects, right? So, but this angle is so small that it just causes total reflection. It just causes total reflection. So basically,
back to
it
my
just
question.
comes out.
So please, back to my question. Where is the point when the biggest light is here?
Under this,
Yes.
you mean the light intensity that's shot out?
Yes. In
There's
the whole-
literally there will only be one track because of light total reflection.
Okay, one disagree with reporters is that only that the point was the biggest light intensity would be impaired before the light started.
I think I misunderstood your question because I thought you
Okay,
meant that
thank
the
you
light
very
shot
much.
out.
Thank you very much. And can you please turn to page 45 again?
45?
Yes, as I've mentioned.
Give it a
And
second.
in page 45, you have a lot of experimental data.
1 second.
Thank
Yeah,
you.
this one.
There's a lot of relation that described in your
Yes.
experiments, is that
Yes,
correct?
yes.
So is there any theoretical model that can prove that the experiment you have done is
Do you want the equation?
Yeah?
We don't have an equation. We
So
only
you cannot
predicted this
quantify-
through relations of cos
Okay,
x and
so-
phi.
I cannot quantify, you cannot quantify your report, is that correct?
Through this, no.
So is there any way that you can simulate or predict the branching light tracks?
The branching light. We can recreate the environment in which the branching light tracks happen.
Okay, thank you. Can you please turn to any page with your experimental data?
Anyone?
Yes. Okay,
This
then.
one, probably.
You mentioned the angle, then how do you define angle since that it is a rapidly changing film,
Maximum.
maximum angle? Then
Yeah,
how
maximum
long
angle.
have you observed?
For each experiment,
Yes,
5 minutes.
5 minutes. And
The-
but you
the
have
time
mentioned
duration
that
is
the
5
bubble
minutes.
will break
Huh?
very soon every time in the short question.
Not like very quick, not like rapidly. We can somehow maintain it to like be there for like 10 minutes.
So
We have recreated
after
it.
10 minutes, you think that the component, since that it is a flowing surface, you agree?
Yes, of
Yes,
course.
so the
That's what
surface
hap-
will become different. Then how can you make sure that the maximum angle is correct? Instead of after 10 minutes, the surface changed. And so your
No, we only
experiment
did the experiment for 5 minutes.
for 5 minutes. So,
Yes, and the bubble breaks.
so you think that
approximately after
in
10.
5 minutes, the bubble surface will not flow?
It will.
It
That's
will.
what causes the rapidly changing.
Yeah, so after a flow, the surface changes. So how can you make sure that the angle, the maximum angle you observe is during this condition? You have
Because
control.
yeah, you have to see the temperature. This one specifically for this one, we have a heating plate that maintains constant temperature of the bubble. So we have to see the bubble flows, but when the
Okay,
bubble
I
flows,
understand, I can,
the
thank you.
the conditions of the bubble doesn't change.
Yes, I
Although
understand.
the distribution
I
of the
understand.
thickness on it.
Please. The next question, how do you think the incident angle will affect the phenomenon?
The
So that's
incident
Thomas
angle.
Sedman mentioned in a small
It will
incident.
it will definitely create a different pattern.
How?
Come here, please. Come here, if you may, if you will. Now, we define incident angle as with see if I shine from here, right? We have like this one,
Yes.
which is the tangent line,
Yes.
and then we shot a laser in from here, and this is the incident angle. Which
Yes.
is, we name it as phi.
Yes.
And then if this is shot in, so if we're just assuming if this is like, this just reflects like, I don't know, right here or something. And this is just an assumption, like it's not real. So if the incident angle changes, if we shoot it from here, if we shoot it from here, then this is fine, right?
Yeah.
So basically, it may like cause a different kind of pattern or
You
something.
can just answer my answer.
Yeah, so it causes different patterns.
Different, how? And the problem also mentioned that only in small angle you can observe the phenomenon. So is there a boundary condition?
Of whether you can or cannot observe the
Yes.
phenomenon. Basically, you would have to calculate the total reflection angle for every thickness, and then
So
you would have
you cannot describe and
for a
clear
certain
direct
condition.
relation
For a
between
certain
incident
condition,
angle
yes.
and whether if you can observe the phenomenon.
for a certain condition, yes.
Yeah, the opponent believes that the reporter failed to demonstrate the boundary condition for whether if the phenomenon will appear. And thank you. And for the next question, how do you make sure that the laser light will go through the soap film in your experiment?
What do you mean that it will
You
go
have
through?
mentioned that the laser light occurs in total internal refraction. Is that correct?
Reflection.
Reflection.
You mean for that one?
Yeah.
Total internal reflection, not refraction.
Yeah. The opponent said correctly. Reflection.
Reflection.
Yeah.
Yes.
Will that happen?
That would possibly happen
Yeah,
if
then
the
ho-
angle of incident
Then
is
how
low
do you
enough.
make sure that the laser light will stay inside the soap film since that your incident angle is not inconstant?
It's not a constant. It is a constant. What are you talking about?
I mean that it's not 90 degrees. The opponent says correctly. Again.
It's not 90. Oh, see, something you're misunderstanding here is that when it is 90 degrees, it doesn't cause any sort of refraction or reflection. It just passes through the bubble.
Yeah.
Yeah.
Yeah. So I mean like this.
For this one,
Yeah.
how do we make sure?
How do you make sure that, okay, if the incident angle looks like this, then why would not the laser light pass through the bubble just like this, instead of it will enter the soap film and create an total internal reflection?
This is a total internal reflection.
Then how do you make sure that it enters? Is
Enters
there any
the soap-
theoretical model
soap-
to prove it?
Soap bubble itself.
Yes?
We see if this is reflected or not. If this does not enter the soap bubble, then it means that this is reflected.
Yeah, so
Right
it
on the
means that
outside.
there is a boundary condition for the total internal reflection
There
to
is.
appear.
There
Yeah,
is.
so why didn't you just mention?
Because you didn't ask me.
Yeah, okay. So there is a boundary condition. Is there any experimental data that can show us?
You have to analyze the thickness of the bubble film.
Okay, thank you. And you have mentioned the refractive index in your experiment, is that correct?
Yeah.
Can you turn to the page with the graph of the change in refractive index? And why do you think it will look like that?
Because when the thickness goes up, right?
Yes.
So basically you have two layers, right?
Yes.
So basically the density of the whole bubble film is higher, and we know that when light passes through something that is denser than the other one, the angle in which the refraction would increase. So that way we can use the Snell's law to determine the n, which is the coefficient.
The opponent disagrees because this graph shows that when the thickness is bigger, it will cause the refractive index that is closer to the refractive index of the water, which is 1.3. Thank you. That is the end of my discussion.
So, opponent, 1 minute to summarize.
As for the summary of my discussion, I believe that the reporter has not mentioned about the boundary limit of the incident angle, and also he failed to demonstrate the wavelength and the random structure that is appeared in his report. And also for the explanation of the main reason for the branching light tracks, the opponent also failed to explain. And for the definition of the correlation length, there is also not a clear definition towards it. And also, the reporter has lack of parameter in his report, which includes the boundary limit I have just mentioned, and the angle intensity, light intensity, which the reporter cannot quantify. And the most important thing is that in his report, although that he has a lot of data, but there is no theoretical model to prove it, and there is no experimental data to prove that the theoretical assumption is correct. And that is the end of my summary. Thank you for listening.
So reviewer have a question to opponent and reporter?
Alright, first of all, I have a question for the opponent. So you mentioned the boundary conditions
Yes.
in your discussion with the reporter. What boundary conditions do you think will cause the phenomenon?
As the problem statement has mentioned, when the when the insert angle is too big, it will not create a phenomenon.
Okay.
Yes.
And also for the reporter, in your experimentation, how did you shine the ray into the film?
We shot a laser.
Okay. And also for your parameters, I just want to ask you, does the density of the soap film affect the pattern?
The what?
The density of the soap film affect the pattern?
The density of the film affect the pattern. Yes.
Okay. And on the theory, how does the thickness alter the index of refraction? Question for both of you.
Could you please repeat the question?
How does the index of how does the thickness alter the index of
Oh, when the thickness increases, the refractive index will closer to water, which is 1.3.
so does that okay,
Yes, I also agree with him.
okay. And also for both of you, does light bend towards the higher or lower index of refraction?
Does light bend towards the higher or lower?
Index of refraction
Index
when it
of-
goes through the soap film.
You mean when it goes through? I don't understand your question, please.
So
What?
so you know how like when light passes through the soap film, okay, so for example, when light passes through like a flat soap film,
Mhm.
does the light bend towards areas of higher or lower indexes of refraction?
Oh, so you're talking about the Snell saw, which we can represent by n1 1 sine theta 1 equals to n2 sine theta 2. And we can draw a diagram, which is this. And so this is
Alright, cool. Thank you. What's your answer for
It
that?
will bend towards the when the refractive index is higher.
And also one last question for the reporter. Could you just define one last time the branching angles and the branching widths?
the branching width is in which the you know how the light when the light passes through the bubble it has like many branches, right? So
Yeah.
basically we take the two furthest branches and we measure the width in between.
Okay. Thank you. That's it.
Alright, for the preparation time for the reviewer. Reviewer.
Since you caused the anyways, you know, the
Talk here. 让他那个 pose 一下，
你可以找到他的资料，
有转过去了吗
找过去了。
Okay. First slide. Okay. So I am Danny from the All-Nighters, and I'm here to review number 9 light clusters. So this is a problem statement, and these are my main focuses. What causes the light ray to branch? How does the pattern of branch flow occur? And also, what are the boundary limits for the phenomenon? So here are the reporter's performance. I thought the phenomenon observation, they had a clear video for it. And for the theory, they mainly concerned themselves with the thickness in the film proportion to the refractive index. They explain caustics and also the thin film interference that helps explain the relationship between the thickness and the refractive index. And for the experiment, they measured the branching angle and width of the branching due to changing the different parameters of, for example, soap concentration, temperature, and wavelength. So for the pros of their presentation, I thought they identified the thickness between the relationship between the thickness and the refractive index very well. They experimented with flat and convex soap films, and they considered the temperature of the film. However, for the cons, I think one big thing is that their theory did not explain the branching of the light qualitatively or quantitatively. They only discussed the film concentration and how it affects the branch width and branch angle. Alright, so this is the opponent's performance. I thought the opponent had a great performance. He proposed good ideas for the theories of the branching of the light, had pros and cons for the reporter. He had a clear progression of theory explanation, explained many parameters that affect the branching, clear speech. But for the cons, I did not think that the discussion of the highest light intensity was very relevant to the branching of light. Alright, so this is the first discussion topic. The opponent asked the reporter, did you analyze light intensity? Where's the largest point of intensity? The reporter said yes, but was not in presentation. So I agree with the opponent in that the point appears right before the light make contact with the bubble. And so the next question is, can you simulate or predict the branching light track? The reporter said that they can experimentally recreate it. I think that the reporter needs to develop some type of theory that is able to simulate or predict the branching light path. Alright, so the next question is, how can you make sure that the maximum angle is what you stated during the changing film? So the reporter measured the average angle. So I think that the average, min, and max angles are interesting values to observe, but I do not think that that may help create the theory that predicts the branchings of light. Alright, next question is, how does the incident envelope affect the light pattern? Is there a boundary condition to which the phenomenon can exist? The reporter said that it causes different patterns. So I believe that there's a boundary condition for the phenomenon, and I agree with the opponent's answer, which I asked him. Alright, so these are the points missed. Actually, the first point was something that was discussed in the discussion. The reporter talked about Snell's law during my questioning, but I thought that during the discussion they could have discussed that point more. And also, the opponent did not give a plausible theory to how the path could be predicted. And also, they did not mention the scintillation index, which is a normalized variance of branch light intensity. I thought that this idea could be able to predict the path of the branching light. And also, I would like to just elaborate on the reporter's idea of Snell's law. Basically, during this derivation, if you derive to this equation, you can sort of see how, like, the reason of how when the light goes into the film, due to the differences in indexes of refraction, you can see how it points towards the higher index of refraction.
Thank you. Reporter, you have 2 minutes to conclude.
Okay, first of all, thanks to the opponent and the reviewer for giving me such fruitful advices. First of all, I would just like to mention that considering that we are doing this experiment and the light passing through the top part of, skimming through the very, very top part of the bubble is really irrelevant to the problem statement. And regarding the boundary limits of the phenomenon, that can be discussed, and let me just quickly explain this. So basically,
in order for the phenomenon to happen, you need to avoid two things. One is the total reflection angle, in which I already just mentioned, and two is that you have to avoid the light or directly passing through the bubble without any reflection or refraction. So basically, you would want to ignore anything that is 90 degrees. So basically, you would just not want to shoot directly into the bubble, and then you would have to calculate the angle at which total internal reflection would happen. And so that concludes my remarks. Thank you.
Okay, so it's time for Julie to ask.
So I have a question for all of you, who's listening here too. I think in the final or for the presentation, you present something like you're using different wavelengths of laser, right?
Yes.
And you found some difference, right?
This one.
Yes.
Yes.
Okay. So, but in the Snell's law, there is nothing related to wavelengths.
Yes.
So what is the reason that you think about?
This Snell's law is not the primary thing that we want to discuss with this PCR array. We just want to make the different wavelengths as a parameter we could discuss. So as you can see, we have to actually let the correlation length be longer than the wavelength of the incident light, which is kind of hard to get. So when the incident light is red light, because its wavelength is smaller, so we have a harder time actually enacting the phenomenon itself.
I think that it's interesting that the reporter chose to change the different wavelengths that resulted in different branching widths and different angles. So I feel like that changing wavelength is not really relevant to maybe like theorizing how the light branches, because that concerns itself with Snell's law. I feel like the changes in branching width and branching angle might be caused by just that the soap film is constantly changing its thickness all over. So that could result in the changes that the reporter observed, which I don't really think are that relevant if I were to report on the question.
The opponent kind of agree with the reviewer that in this parameter is irrelevant with the topic, and for the reason for the experimental result to change may be because, as the reviewer has mentioned, that the component inside of the soap film. Sorry.
The final question, please. And for the red and green light, which one has longer wavelength?
Which one has a longer wavelength? Green.
Which one?
Green. It's written on there.
Please check it.
Oh wait, no, not red. I switched it. Oh my god. No, wait.
Other questions?
That's narrow, I'm sorry.
Other questions?
Okay, question for the opponent and reviewer. You guys all talk about the model lacking in his report, right? So do you have any model in your mind?
If I was to go first, I think on my very last slide, there's a short equation that I wrote here.
So it's pretty complicated how you would derive it, but if you look at the expression on the right, the x and y, if you plotted it, it could possibly be a theory that could predict like the branching of one single light ray.
Yeah, the opponent believes that through that way, it may be able to predict the light branches tracks, but it is also very complex since that the problem statement mentioned it is rapidly changing and the surface is flowing, so it is kind of hard to predict the refractive index change.
So no model.
Yeah.
Your answer.
Can I add on to my answer? And also, in my previous slide, I think the scintillation index, which analyzes, as you can see here, like basically like the different intensities in the light that causes the branch flow. I think that analyzing, like, you could possibly take pictures of the topology of the thickness of the soap film at different areas to possibly like simulate that to predict like the branching of light, because the branching of light is correlated with how thick the cell film is at different spots. Yeah, so I think that using that, it could be a good prediction model.
Alright.
I don't have a question, but I just need to see your schematic on page 8 once again.
Page what again?
Page 8.
Page 8.
Yes. Okay, thank you.
Oh, okay.
Okay, thank you. So now it's time for curious quiz. Okay, so now they show the points for reporter. Starting from me. Okay. So 7, 6, 6, 6. Sorry, once again. 7, 6, 6, 7, 6, and 7.
Very much.
And now it's for our opponent. Again, there's a 7, 5, 7, 8, 8, and 8.
Thank you.
And finally, for the reviewer, I got also 7, 8, 7, 8, 8, and 8. Okay, so anyone want to comment? So if not, expect everyone, let's close this stage. Then we have 15-minute break. Going to be presented problem number 6. And sometimes you can write down the name of the representative.
trades and fellow competitors. This is Team here, and today I'm going to report problem statement number 6, a reversible Cartesian diver. The problem statement is a simple Cartesian diver. For example, an inverted test tube partially fills water, is placed in a long vertical tube fills water. Increasing the pressure inside the tube forces the Cartesian diver to sink. When it reaches a certain depth, it never returns to the surface, even if the pressure is changed back to its initial value. Investigate this phenomenon and how it depends on relevant parameters. And the main focus we investigated was the force analysis during different sinking stages and the certain depths for irreversible situations. And this is my experimental outline. First, I'll show my preliminary experiment and theoretical model. Finally, will be the experiment, discussion, and conclusion. This is my observation video. As you can see, when we increase the pressure in the long vertical tube, the diver sinks to the bottom. After a period of time, when we release the pressure, the diver will return to the water surface. And when we increase the water inside the long vertical tube to a higher level, the diver also sinks to the bottom. However, even if we release the pressure, the diver will never return to the water surface. And the following report is going to discuss and demonstrate this phenomenon. And let me start with the preliminary experiment. And this is our observation. In our observation, we have observed that during the sinking stages of the diver, the water will rise in the inner water level. So we used tracker to analyze it and found that there are two main stages during the sinking. For the first stage, the rise is more significant, which is mainly caused by the increased air pressure in the water pressure. And for the next stage, the velocity of water entering the diver decreases, which is mainly caused by the water pressure. And since that the inner water level will affect the buoyancy and density, therefore we predict that this may be the main reason for the diver to create irreversible situations. And for the qualitative explanation, according to the Boyle's law that PV equals in constant, therefore when the diver sinks, the pressure increases, which decreases the volume of the air column. As we all know that the buoyancy equals to the mass of the outlaying fluid, therefore when the diver sinks down to the bottom of the long vertical tube, the buoyancy also decreases. When the pressure is changed back to its initial value, as the problem statement has mentioned, the delta P will equal 0. And there are two main forces that affect the motion of the diver, the buoyancy and the gravity. If the gravity is bigger than the buoyancy, it will create irreversible situations. And the next part is our theoretical model. In our theoretical model, there are some basic hypotheses that the air column fits the ideal gas, and our water is incompressible. And also, the outer water level will not change in our experiment, and we ignore the bottom plate since that it is very thin. And this is our theoretical model of the Pascal law. We use the Pascal law to describe the phenomenon that the pressure was transferred from the surface of the long vertical tube to the diver. And using the Pascal law and the Boyle's law that the PV equals constant, we're able to calculate the pressure inside of the diver, which is the atmospheric pressure plus the additional air pressure and the water pressure. As we know that the cross-sectional area is in constant, therefore the length of the diver will also be inverse proportional with the pressure. After simplifying the equations, we can finally get L, which is the length of the air column. And this is the theoretical model when the diver is balanced. As I have mentioned that the gravity has to be bigger than the buoyancy. Therefore, we can draft this equation that shows the mass of the outlaying fluid. After simplifying this H, we can finally get the certain height for the diver to create irreversible situation when the pressure has not been released. Before the diver got balanced, the drag force will affect the motion of the diver. And as we all know that the Reynolds numbers has something to do with the drag coefficient, therefore we simulate the Reynolds number versus time through its graph. And as you can see, it fits the laminar flow. And after transforming the Reynolds numbers into the drag coefficient, we're able to calculate the value of the drag force. After knowing all the forces, we're able to draft this equation of the total force, which is composed by the gravitational force, drag force, and the buoyancy during the sinking motion of the diver. When we get the force, we can simulate the sinking motion of the diver, and the results looks like this. And the simulation will be used in further discussion about the comparison and our theory data. And for the next part is about the Bernoulli's principle. As we all know that the potential energy plus the kinetic energy equals in constant. Therefore, we'll assume 2 points, which is point A and point B. As I mentioned that the outer water level will not change, so the VA equals to 0, while the H also equals to 0. After simplifying the equation, we can finally get this equation that shows the value of VB, which is the velocity of water entering the diver. And after transforming the velocity of water entering a diver to the quantity, and for the decreased volume, we can calculate the buoyancy through this equation. And finally, you can once again get the force, which is mentioned in this equation. And we can once again simulate it by this total force. And as I've mentioned that we assume it is an incompressible fluid. Therefore, the result of the theory derivation proves our assumption and once again confirm our theory. And for the next part is the certain depths for irreversible situations. As I've mentioned that when the pressure is released, the inner pressure inside the diver will turn into this, which is the atmospheric pressure plus the air pressure. When the pressure is released, the delta P equals to 0. We can once again list the force equation and get H, min, which is the boundary condition, or the certain depths for the diver to create irreversible situations. And the next part is our experiment. In our experiment equipment, we use plastic tube, test tube, inflator, lead sheet, and barometer. And this is our experimental setup. We use the inflator to increase the air pressure inside the long vertical tube, and use the test tube as our diver. The whole system is connected with the barometer and a released air flow, which can control the air pressure inside. And for the next experimental setup, I'm going to demonstrate how we measure the critical height to create irreversible situations. We use less water in the beginning and increase the pressure to force the diver to sink. After we release the airflow, we realize that it returns to the water surface. Therefore, it means that during this point, it will not create irreversible situations. However, when we increase the water to a higher level and forces the diver to sink again, when we release the airflow, the diver no longer returns to its initial position. Therefore, the height above this point will all create irreversible situation. And the later discussion in the graph will look in this form. And for our experiment one is about the certain depths for irreversible situations. And these are the parameters, including the depths of the position of the diver, the length, cross-sectional area, and the mass of the diver. And our first experiment is the length of the diver. We have all variables controlled, and this is our experimental data. As you can see, when the length increases, the depth of irreversible situation also increases. It is because that when the length is larger, it will create a bigger volume of the air column. Therefore, it requires larger water pressure to make the diver maintain at the bottom of the long vertical tube. Therefore, the length and the depth has positive correlation. And as you can see, there is a serial limit in the beginning of the theory data. This is because that when the length is very small, the diver will sink directly into water. And our next experiment is about the cross-sectional area. We have all variables controlled, and our parameter is the cross-sectional area of the diver in inner cross-sectional area and outer. And this is our experimental data. As you can see, when we increase the area, outer area, the height increases. It is because that when the outer area increases, it will cause a bigger volume of the diver, which requires a larger water pressure to maintain the diver at the bottom of the long vertical tube. Therefore, the outer area have positive correlation with the critical height. And our next experiment is about inner area. As you can see, when the inner area increases, the height also decreases. It is because that when the inner area is bigger, it will create smaller volume of the diver's volume. Therefore, it will no longer require so much water pressure to make the diver maintain at the bottom of the long vertical tube. Therefore, they have negative correlation. And our next experiment is about the mass. We have all variables controlled, and our parameter is the mass of the diver. As you can see, when the mass increases, the certain height decreases. It is because that larger mass will cause larger gravitational force, which makes the diver no longer need so much water pressure to maintain it at the bottom of the long vertical tube. Therefore, they have negative correlation. And our second experiment is about motion during sinking. Our first experiment is the time. We have all variables controlled, and our parameter is the time of the pressure maintained. As you can see, the longer the time passes, the deeper the diver sinks. And every time will represent a certain height in our experiment. After the time that represents the critical height for create irreversible situation, the time above, beyond this point will all create irreversible situations. According to our theory, you can also observe the relation between the T and the buoyancy. And through these two equations, you can know how we simulate our theory lines. And our final experiment is about the air pressure. We have all variables controlled, and our parameter is the additional air pressure. As you can see, when the pressure increases, the depth also increases. It is because that larger pressure will cause larger deformation of the air column. Therefore, the depth will also increases. So they have positive correlation. According to our theory, you can observe the relation between the buoyancy and the additional air pressure. And by these two equations, you can see how we simulate the experimental result. And finally, it's our conclusion. As I have mentioned that according to a Bose law that the PV equals constant, and when the diver is sinking, it will create a larger pressure which decreases the volume of the air column. After simulate the buoyancy in our equations of forces, we can know that the buoyancy would decrease as the diver sinks down. After simplifying all the equations in the simulations, we are able to get the H-min, which is the boundary condition or the critical height for the diver to create irreversible situations. And for the next part, which is about the simulation, as I have mentioned that the result of the Bernoulli's principle and the total force looks like exactly the same. Therefore, the drag force can be ignored, and our assumption of incompressible fluid and non-viscous fluid can be accepted. And it proves and confirms our theory. And as I have mentioned that there is a boundary limit in our experiment that when the h is smaller than 0, which means that when the diver sinks directly into water, we cannot observe the irreversible situations. Therefore, the possibilities will only be able to observe over here. And to re-emphasize our experimental data, as you can see, when the inner area and the mass increases, the certain depth decreases. It is because that it will no longer require so much water pressure to make the diver stays at the bottom of the long vertical tube, which means that the mass in the inner area have negative correlation between the certain depths. And finally, the outer area and the length has positive correlation with the critical height for the irreversible situation to happen. It is because that when they are bigger, it will require larger water pressure to make it maintain at the bottom of the long vertical tube. Therefore, the length and the outer area has positive correlation with the critical height or the boundary limit for irreversible situation. And this is the end of my presentation. Thank you for listening.
Okay, so it's time for opponent expressions.
Okay, thank you, reporter, for a wonderful presentation. I will start off my first question by clarifying that you increase the pressure by pushing a pump, right? Yes. Is the pump sort of like a bicycle pump where the more you increase it, the higher the pressure, or does it have levels where you can change the levels? Please turn to page 22. Yeah, as you can see, when we push the pump, it will increase the pressure. And so you're basically like pushing the pump? Yes. Okay, second question. And from your animation, I didn't see clearly, I saw a demonstration of the phenomenon, but I didn't see it from the top. Did you start the dive from the top level of the water? Please turn to page 5. And actually, the diver is at the top of the longer tube. Is it touching the surface of at the top level of the water? Yes. Okay. So did you account for the surface tension that can occur when it's at the top of the water? As I have mentioned that in our theory assumption, which is page 13, that we assume that it is an incompressible fluid and non-viscous fluid, so the surface tension can be good. Okay, thank you. You mentioned that you were changing the pressure, but yes. According to the ideal gas law, PV equals nRT, so when you increase the pressure, the temperature should increase. We also mentioned that you made the temperature constant. How do you account for this? Actually, we use the diver without putting it into water and increase the pressure inside of it. And realize that the temperature inside will not change a lot. Therefore, we believe that the temperature rise should be able to ignore. Okay, so another clarification question. How are you able to make sure if you're viewing from the side that the diver doesn't touch the sides because we know that the tube is okay? You mean the long vertical tube? Yeah. I believe that by touching the side of the vertical tube will not affect the critical height. Question. What's the material of the altitude and the diver? Plastic? Plastic, okay. Yeah. Thank you. So I can make sure what because that
Just like, so I want to clarify, do you think
Oh, so for example, I think do you can clarify, do you actually think that
What's the core concept of make sure that all the food experimentation. Just make sure that yes. Maybe like 1, 2, 3, then just do 3. Majority. Show you understand theoretical. You can just say like so like regarding the theory, so yeah. Regarding like the main concept.
Next thing I'd like to also
Okay, thank you. This is my opponent presentation for the reversible continuum diagram. The problem statement is very simple, you can read it yourself. The first thing we'd like to discuss, the ideal structure investigation is first, what causes the diagram to sink? The second, what are the parameters that actually affect the depth to which it sinks? The third is how do the relevant parameters affect the depth and or the other parameters? Okay, so here are some pros and cons of the report. The pros are that there is a clear footage of the phenomenon, even though it only occurs for a specific point, which I think is a little bit shady. The second pro is that there is clear intuitive explanation of the phenomenon, and it also accounted for specific parameters. However, there are some cons. First of all, the footage of the phenomenon at the top part isn't so clear, so you can't really see what's going on top. Second is the temperature gradient, I'm not sure how they accounted for it. Third is the tube is very thin. I'm not sure by pushing or pumping, and I'm not sure how they made the diagram uniformly dense. I didn't know what material they made it. It wasn't very clear, but I'll clarify that later. The next one is that they assumed the air to be an ideal gas. Fourth is the surface tension, because they mentioned that they started at the top even though they said it was negligible. I would like to disagree with that. The second to last one was that they assumed the diagram and the bulb has uniform density, which I mentioned earlier. And the final one was there was an unreliable way of changing the pressure within the container. Okay, so the points to be discussed are, of course, the parameter, where we'll discuss the pressure, the temperature, the air amount, the mass of the diagram, and as you mentioned, drag. And we'll then go on to experimental setup, and we'll discuss how well their setup demonstrated the parameters and also the accuracy of their setup. Then we'll move on to theory, where we will discuss drag, what they think of drag, the surface tension that occurs at the top, the temperature which occurs when you increase the pressure, and the friction between the diagram and the tube, which because it was made of plastic and it was very thin, I think it was, yeah. And I would like to start our discussion. Thank you. Okay, thank you again for a very good presentation. First thing I would like to clarify again is for when you increase the pressure, yes, one parameter you tested was pressure, right? So we were trying to find how, if a larger pressure was applied, how the maximum depth you can go, how it will increase or decrease, right? No, actually, can you please turn to page 37? You mean this experiment?
Yes.
Actually, we have the time control. So we have different pressure that is added in the one for two.
Yes,
I understand that point. But my question is, since, for example, if you were applying a larger pressure, if you want to push it down to achieve a larger pressure, you also have to go through smaller stages of pressures. How do you ensure that as when you press it down completely, it immediately achieves that pressure, but doesn't also go through the other smaller pressures? 22. Yeah, as I mentioned that there is a barometer that can control the pressure inside of 1.2, and most of my pressure that is mentioned in my experiment can be achieved by only one push. So the phenomenon that the opponent has described will not happen. Okay, I see. Thank you. Also, as I mentioned earlier, how did you consider you didn't consider temperature to be an important parameter in this experiment, right? Yes, as I mentioned that. Do you consider viscosity to be an important parameter? Sorry, do you consider viscosity to be an important parameter in this? Please turn to page 17. Yeah, as I mentioned that we use the Bernoulli's principle, and the basic assumption of the Bernoulli's principle is non-viscous fluid and incompressible fluid. Therefore, after looking at two results, you can see that they look very similar. So which means that the drag force or the factors that the opponent has mentioned would not affect my actual experiment. Yes, I agree with the viscosity part, but you are aware that by changing the temperature, you do change the viscosity. Yeah, as I mentioned that the temperature rise is very small, that can be ignored. So therefore, the viscosity that is caused by the temperature rise should also be ignored. But even if it is ignored, can you give a specific number? For example, the area, why can it be ignored? How small is it? Do you want me to predict what will happen if the viscosity rise, or? I would like you to give a proof for your statement that the temperature isn't a big factor in this. Yeah, as I mentioned that we take the diver out from the long vertical tube and add the pressure inside of it, and realize that the temperature inside of it did not increase a lot. And also, the diver was dropped inside water, so the water should be able to. Sorry, I don't think that answers my question. Do you have a number that compares the different temperatures to see if they don't matter? No, we don't have that in our experiment. Okay, that's okay. Or I think that is unnecessary. Sorry, I wasn't sure if I caught this, but do you have a graph of like the depth versus time for this one of your? The what? Depth versus time. That's for an example. Can you? Yeah, this is the depth versus time. I would like to ask, is that a theory curve? That is the simulation curve by our theory. So kind of. So can I see a data curve, please? Excuse me? A curve based on data. Do you have like data? Based on data. Yeah. Do you have data? Turn to page 5. 8. Yes. So where are your points? You asked me to show. Wait, sorry. Are each of these things a point? Yes. So you basically track the variable. You use track. So what function do you think this represents? I don't think it is representing anything because it is an HT chart. Okay. And if you are asking me for a BT chart, the reporter believe that it will rise. The acceleration will rise at the beginning, and at last the acceleration will equal to a constant. Sorry, did you say the acceleration will be positive at the beginning? Excuse me? Did you just say the acceleration will be positive in the beginning? Will rise. So you're saying the diver rises up at the beginning? I mean, the acceleration rises instead of the diver. The diver sinks. The acceleration rises. You're saying the diver speeds up at the beginning? Yes. Okay, thank you. I would like to, can you go to your drag force? Drag force. Please turn to page 16. Sorry. Okay, this is, first of all, let me clarify, why do you consider drag force to be an important parameter in this experiment? Because not only does the reporter want to discuss about the critical height of the original situation, I also want to discuss about the motion during the sinking. So therefore, during the motion, the drag force should be considered. Yes, I agree with that. I agree with the part that during the motion, the drag force opposes the velocity of the diver, which I agree with. But one thing I want to mention is that I don't think the viscosity of the liquid affects the maximum depth to which it will sink. I agree that it affects the velocity to which it attains that depth. I don't think it actually. Yeah, it will not affect the boundary condition. It will not affect the boundary depth. Yeah, so I agree with you. This drag force should not be in the maximum depth equation. Excuse me? This drag force shouldn't be in maximum. Yeah, as you can see at our final page, this is buoyancy, and this is buoyancy of the diver. This is buoyancy of the column, and this is gravity. There is no drag force included. Okay, sorry. So let me clarify. Is not good. Oh, please turn to page 50. And this is my backup page. Since that when the diver drops into the water, it will create an initial height, which is h0. We define it as h0. So the initial height inside the diver will not be the length of the diver. There will be an initial water level inside the diver. Therefore, in our series calculation, we should put L0, which is defined as the initial length of your column. Should be. Okay, now if you go back to your experiment and data slides, you can obviously see that there's some obvious error and deviation. How do you think that account for that deviation? Do you think the temperature or the viscosity actually plays a role in that deviation? Please turn to page 30. Yeah, as you can see that the series line actually most of them crosses between the circles and the x. Right, sorry, what are the circles? As I've mentioned, please turn to page 23. Yeah, at the beginning of the experiment, we use less water and make it to sink. Sorry, my question was what are x's and what are x's? Yeah, and explaining. Yeah, so when we release airflow and it returns, it means that it will not create an irreversible situation. Since that we are not able to know the boundary condition, which is the exact number for this phenomenon to occur. So we have to get very close to this situation. So there is two kind of situation, which is will not create a irreversible situation, and that will affect the. Okay, one thing I want to mention is that when I asked for the error graphs, you gave me a graph with actually relatively little error. Can you turn to your graph size again? Can you provide a page number? I don't have the page number, but I'm sure you know what you're explaining, where you're explaining those sides are. 27. That's what you want? Kind of. Can you turn to the next another one? Sorry. Right, for example, on this, so just to clarify, this is the theory curve and these are the actual. Yes, the actual experimental weapon. Wait, so how do you account for these being higher and this actually being lower? How do you account for these errors? Because we change the area of the diver, and which may cause some differences. Because when this is the inner area. Change the area. Sorry to interrupt. Of the diver, then is it included inside your theory? And if it is included inside your theory, then shouldn't your model be presented? Yeah, it is representing it. It is very close to your experimental data. Because that every experimental data, which is the circle and the x, in between there is only 5 centimeters, which is very small. So there may be some experimental errors to occur. And I believe that the theoretical model still fits to our experiment. To clarify, I would not take 5 centimeters as a very small depth, but I guess that's okay. So you also mentioned that apart from measuring the maximum depth you think the Cartesian diver is able to attain, you also wanted to measure the rate of change, the rate of the Cartesian diver to which it attains the maximum depth. Can you show that to me? I don't understand your question. Can you repeat again? You mentioned that you wanted to measure the maximum depth to which the diver was able to go. And you also mentioned I did not mention. So you don't want to figure out how deep it is able to go before it sinks? Before it sinks? Before it sinks, it stay at the top of the long regular tube. Before it sinks, before the diver sinks. Do you understand this problem? It's like at a certain depth, it's not going to come back up again. Yeah, and then also this is what the certain depth is. So basically, like this depth. You also, apart from measuring the exact point of this depth, you also wanted to measure how fast this reaches this depth, which you explained with drag. Yeah, yes. Actually, yes, you can say that. Can you show me where your rate of change, rate of diver equation is? Rate of diver equations? You mean our simulation? Not your simulation, the actual data. The actual data. Is that show? Page number 5. Yeah. How's that show? I think this is a. No, I'm asking for velocity versus time, not height versus. Page 16. Velocity versus time. So you think the velocity is changing proportionally at a linear rate with respect to time? In the beginning, yes. I would actually like to disagree with that. I think actually the acceleration changes with the depth because the weight of the water actually changes it. The reverse is correct. That the velocity will reaches in the same acceleration at the. Wait, sorry, could you repeat that again? I'm not so sure. I mean, the reverse is correct. That the velocity will increase in the same acceleration in the back of the sinking motion. Can you justify this using model? Yeah, sure. Because when as I've mentioned that the water will increase in order. Oh, I'm sorry, you can okay. Yeah, it will increase in order. So it will be very close to zero in the volume inside. So which makes the buoyancy only left the volume of the diver. So I'm not sure due to your image, but if that were true, then can you skip to the side row of previously? If velocity versus time is linear, then shouldn't this graph be quadratic? How do you account for this in the graph? What do you mean? Shouldn't it be quadratic if you think the velocity versus time is linear if you integrate it? Yeah, it will also decrease in, no, it will not be a constant, but yes, as you have mentioned that when the velocity gets faster, drag force will also be much larger. So it will not be perfectly a constant for the acceleration, but it will be very close. Since that, as I have mentioned, the drag force can be linearly ignored because of the confirmed by the Bernoulli's principle and the total force in my theory direction. Okay, I think that ends our discussion. Thank you.
According to 1 minute to the
Okay. The reporter and I had a discussion where we discussed the rate of change, which at the end of the Cartesian diagram we discussed how apart from attaining the maximum height, he also measured the rate of change, which he incorporated drag force into. At that point of interest, I'd like to disagree with the reporter. I think drag force has no effect whatsoever on the maximum depth it attains because it only affects the velocity, but not the maximum depth. Also, we also discussed the added pressure of into the tube. He mentioned that he was able to have a categorical increase in pressure, which I thought was a little bit shady because even if you had a categorical increase, you would have to go through various different pressures to attain that maximum pressure. And during those little pressures, you can certainly measure a certain decrease in the diver, which would not be accounted for.
It's time for review of the next question.
So, my first question is for the report. Please turn to page 16. So, what's the unit of the acceleration?
Acceleration?
Is it meter or centimeter?
Centimeter. It's meter.
Meter. So, according to the movement of the acceleration will bring is half of a times t squared, right? So if the unit is meter, so it will move like to 20,000 meters. So how are you supposed to prove that? Here it will become a constant.
What do you mean? I don't.
So like there's an easy equation for this, right?
Yes.
So if we put a like 4, and as t is 100 seconds, right?
Yeah. Actually, the diver would not sink for 100 seconds. That is only the simulation.
So yeah, whatever. So this is equals to 1,000, that's 20,000. So
after 100 seconds,
yeah. So are you able to do that in your laboratory?
No.
So how are you going to prove?
As I mentioned, that the diver would not sink for 100 meters since that
So
there is some limitation.
So did you do 100 meter, 100 seconds?
No, we did not.
Okay, so my next question is for both of us, but the report first. Will the shape of the diver influence your result?
The shape of the diver.
Yes.
We did not do further investigate in our report, but in our experiment we control the shape of the diver.
What's your opinion about that?
As they use a relatively thin tube, I think the only way for them to change the shape of the diver would be to elongate it, which I don't think will change. Obviously, if they put something on the bottom, that will change the drag force, which, to be clear, will not change the maximum depth, but will certainly change the velocity to which it will attain that depth.
Okay. So my next question is your tube a rigid body?
Excuse me?
Is your Cartesian diver a rigid body?
Yes.
Yes. So it wouldn't have any change in its shape.
No.
Okay. So what's your opinion about it?
Yeah, I agree with the report.
Okay. So my next question is please turn to page 20. So as the opponent mentioned, in this graph, this part of it.
Yeah.
So what may bring the deviation? So there are there are two process.
Yeah.
And you mentioned that each process is 5 centimeters, so it equals 10 centimeters.
Yes.
It's 10 centimeters like this. So what do you think? What do you think?
Sorry, time's up.
Okay, so I'm the reporters from Team Acquisition, and the topic is number 6, reversible constant diagram. And here's the outline of the report. First, in the observation, it's clear and concise. In theory part, the mathematical parts are aided by diagrams for the audience to understand it easily. And setup part, the animation is clearly explained in the experiment. However, some real footage shown would have made it clear. And the experiment part, it's easy to understand, of course. And conclusion part, the conclusion is in sync with the theory. Next slide. So here's my brief review for the report. So the pros are it's very clear structure, detailed mathematical parts, and overall success regarding experimental results. And some small details have been missed and need to be explained. For example, change of viscosity due to temperature. Next one. So for the brief review of the opponent speech. So the pros are concise and clear questions for the report. They show logic and precise discussion regarding the experiment. However, they're not of great importance since the results do not show signs of them being influenced. And you spend too much time discussing some problems which was in the report, and there are no directive advices were given. So here's a discussion between the reporter and the opponent. So the first question is, how do you ensure that the pressure is ensured when it is changed? And the reporter says that a barometer can fix this problem. So my real point is a more precise method should be developed. So the second question from the opponent is, there's no consideration of temperature. Was viscosity put into account regarding temperature? And the reporter answers that viscosity was summarized through Bernoulli's law. And the reviewer's point of view is that the change of viscosity should be also put into account. Yes. So the next question from the opponent is, are there numbers comparing to the temperature? And the report says no. So the reviewer's point of view is that the reviewer agrees with the opponent that the temperature should also be considered, or you should do some experiments to prove that. The second question from the opponent is, drag force should or not be included in the equation, and the report says that drag force was not included. So the reviewer's point of view is that we agree with the opponent. The drag force does not affect the maximum height, only affecting the velocity. So the third question is obvious errors in derivation in data, for example, in page 37. So the answer from the report is that the area of divers was changed, so differences might be generated. And the real's point of view is that the research agrees with the opponent that 5 centimeters indeed is not neglectable, and further data analysis should also be conducted. So here's my short advice for the reporters. So maybe you should conduct more experiments next time. So for example, in page 37, there's huge deviation between the theoretical and your experimental data. So that's all I want to say. Thank you.
Okay, so it's a final remark.
And for concluding remarks, and as I mentioned in the theoretical model, that there is a simulation of the sinking motion. And as you can see, it can be described of the total force. And there is a simulation, and these are all just simulations. And the 100 second will not reach in our reality. So therefore, the simulation still fits to our experimental data. And for that phenomenon will not happen in our experiments. And as I've mentioned, the main reason for the irreversible situation to happen is because of the Boyle's law and Pascal law, that the PV equals constant, and the velocity, the volume of the air column will decreases, which makes buoyancy also decreases. And finally, we can get the H-min, which is the critical value or the boundary limits for creating irreversible situations. And as I've mentioned in our experiment, that when the parameters increase, which will cause the air column to increase, it will have positive correlation, since that will no longer require so much water pressure. And this the remark in the further discussion. And about the temperature that the opponent has mentioned, that it can be ignored in the experiment, and the reporter also have a way that can confirm that it is able to ignore it. And also, the theory considered the water as incompressible fluid and non-viscous fluid. And the Bernoulli's principles and the simulation prove this assumption is correct. And also, the drag force is important to affect the motion of the diver, but it will not affect the final height to create a reversible situation. So the opponent may have some misunderstandings for this concept. And also, the deviation between theory and experimental data, but the trend is also the same, which means that our theoretical model fits to the experimental data, which has been considered a lot of factors. And the velocity will not increase in the same acceleration due to the drag force, and we do not consider the shape of the diver. Finally, in real situation, the diver won't sink for 100 seconds, and the graph is only a simulation, which fits to our experiment. Thank you for listening.
Okay, so shall I start the question from the jury?
I have one question for all of these answer carefully. According to the kinetic theory of gas, PV equals ln of T. The pressure is proportional to temperature, right? So from your opinion, the temperatures affect the final result at a certain time?
Actually, when the pressure increases, the volume also decreases, and some of the increased pressure will turn into the decreased volume, and some of them will turn into the increased temperature. And after observing, we believe that the ratio between them, that the increased temperature is very small and can be ignored. And also, the diver is placed in a tube with water surrounding it, so the temperature may cool down very soon, so that the temperature in our experiment can be.
So my point of view is that if the change in temperature is only slightly, it won't bring huge effect to this phenomenon. But if the change is like 10 degrees Celsius, it may bring huge effect to the phenomenon. Thank you.
I actually agree with the judge's point of view. As I mentioned during my discussion, I brought up PV equals nRT and also mentioned that changing the temperature changes the pressure. Obviously, the reporter made sort of a point saying that temperature is negligible, but obviously he didn't have any data to support this. So, yeah.
Other question? Alright, so I have a question for the reporters, and also I want to hear the opinion from others. So in the concluding remark, the final point you say you did not change the shape, but you control it. What does that mean? Or the shape? What's the effect of the shape in your experience?
It means that in our experiment, although we did not use shape as a parameter, but in all of my experiment, the shape of the diver is circle. That means that we control this variable, that it will not affect the experiment. But if the reviewer really wants to discuss about the affection of the shape, the reviewer believes that it will only affect the volume of the air column and also the drag force, because there is an A in the equation.
Okay, how about the opponent?
Did you ask whether
Will the shape of the tube play any role in this, or what,
well,
or importance?
well, I mentioned before that I don't consider drag force to be a part of attaining the maximum depth, and I believe that changing the shape of the diver it can change the mass of the diver. I think mass plays a big role in changing the depth. But if the mass doesn't change and only the resistance changes, I don't think that will change the maximum depth to which the diver can attain.
So I agree with the opponent partially because I believe that the change of the shape is going going to change the critical height and the other data, but I think that the trend of the Cartesian diver, irreversible, is still the same.
I need to see one figure again. You have a slide showing a theoretical model about drag force in the two figures.
Page 15.
Yeah, this one. What is the right figure? Can you? What is the right figure?
This one?
Here. I cannot read very clearly.
Oh, in the y-axis is the drag coefficient, and
The
in
coefficient, okay.
yes, and in the x-axis is the Reynolds number.
And so that's from your measurement, or?
Oh, that is in the reference that we mentioned in the backup page that this graph is the data is from the internet.
From what?
From the internet.
Oh, it's not the measurement.
Yeah, it's not
It
the
looks like a measurement. Okay, fine.
sorry.
And the opponent, can you show your slide again about the pros and cons of the reporter? Right. Can you tell me what you mean by clear footage of the phenomenon and footage of the phenomenon isn't so clear? What do you mean?
Oh, because this is actually a sort of double-edged part. First of all, they only show one video of the phenomenon, and they only show the bottom. Maybe it isn't even half of the phenomenon.
Do you mean different thing, or I don't understand?
I mean, they only showed half of the phenomenon, but the part they showed was pretty good.
Still don't get it.
Okay,
Can I clarify that point?
No.
Okay, fine.
I think it's fine. Oh, you ready? Okay. Okay, so there's show the point for reported. Very consistent. 7, 8, 8, 8, 8, and 8.
Thank you.
Good point. And also opponent. Also quite consistent. Yeah, 7, 8, 7, 8, 8, and 8. And finally for reviewer. Yes, 7, 8, 7, 7, 7, and 8. Yeah, it's a good fight. So that concludes our fighting, and thank you all.
I have one comment.
Okay.
Yeah, just comment. I mean, I'm looking at the PowerPoint that you have made, and it seems that well, I mean, actually, I think all the three teams have very good presentation of the PowerPoint. I mean, it seems that most of them that there is no citation. So I mean, your theory or your data or your figure, if it's not your own, then it's better than the reference. And that actually, I mean, maybe sometimes you think that if most of them are from others, or for example, secrets or whatever sources they keep, and it might reduce your contribution. I mean, I think honesty is a good thing, and then most judges will realize that. I mean, you guys are just high school students. It's almost impossible for you to derive everything. And it's fun to use people's theory or graph or just cite it in your PowerPoint. And that, because if you look at you guys all have these score chart, and they are special. I mean, if you cite it, actually increase your point. It's not going to reduce your effort. That's my only comment.